Okay, so today I will present a work of four authors, which is titled as Disentangling Images with Lie Group Transformations and Sparse Coding. So this is a very neat and short work, which is done by the authors, and I will present motivation, key algorithmic details, limitations, and finally key takeaways in this presentation. So to start with the motivation, so how do humans learn to recognize transformations in visual scenes such as rotation and scaling that are independent of object identities? So the question of how to form representation of images that disentangle visual transformation from objects is of interest for both of like neuroscientists and computer vision scientists. So rather than using neural networks, very complex multi-layer neural networks like variational autoencoders with some additional laws, the authors have developed a Bayesian generative model that is capable of learning the continuous transformations as well as discrete patterns in the images. Specifically, they have used MNIST in this case in an unsupervised manner. So here, authors propose a novel unsupervised algorithm that is Lie group sparse coding that combines the advantages of mathematical modeling and signal processing. In particular, their work is much inspired by previous work that introduces mathematical framework of representation theory to disentanglement learning. So authors build on this framework by including a latent representation of shape via sparse coding. So basically, the proposed algorithm says that the sparse representation of shape and its transformation from an image can be learned by specific dictionaries. So such that like each of the MNIST digit is learned as a specific dictionary, and this process is done by iterative process expectation maximization, which is they have termed the same way in their paper. So they demonstrated like the capacity of the model to disentangle representations of shape and transformation from controlled datasets. So specifically, they have used synthetic datasets where they have modified the MNIST dataset with transformations and translations, and the shape, categories, and factor of variation due to the style are unknown and must be learned from the data. So the goal is like the from the full MNIST dataset where both the underlying shape categories and factors of variation due to style are unknown, and that must be learned from the data. Now, with the respect to key algorithmic details, so the author represent the image. Let's say, for example, one image is represented as the space from dictionary, and it is represented as a combination of W vector, that is the orthogonal set of orthogonal vectors, and along with that, the phi and alpha are added. So phi is basically your dictionary, and alpha is the sparse coefficient. So basically, each template or column of the dictionary, the image dictionary, has L2 norm that ensures that each discrete pattern is qualitatively unique irrespective of scaling, because we are actually adding the translation and scaling in our further steps, because each image is transformed and translated earlier before training. So this is the training algorithm. Like the learning algorithm starts with the initialization of model parameters, where the coefficient vector alpha is initialized as IID, that is the exponential distribution, random exponential distribution, which is independent. Each dictionary template has an L2 norm that preserves the qualitatively unique features without any scaling error. So the learning algorithm starts with an initialization of random parameters, sparse coefficient alpha, that is initialized with IID, exponential distribution random variables. And for image I, we want to actually get the sparse code alpha and transformation parameter S, such that for the batches, we want to learn parameters such as W matrix, and phi is the dictionary with L2 norm by maximizing the log likelihood. So maximum a posteriori estimation is calculated with the gradient descent algorithm, that is this the maximum posteriori maximum likelihood is calculated, and then the final approximated gradient is calculated, which is also the previous work of Fista, that is fast fast iterative shrinkage thresholding algorithm for linear inverse problems. So they first take expectation, like in the step 7, they take the expectation of the joint density by marginalizing with respect to S, and take the gradient of the remaining expression that is still a function of alpha, which is our sparsity, right? Sparsity value. And this gradient is used they calculate the gradient for alpha and update alpha using Fista algorithm, which is the previous work for fast iterative shrinkage thresholding algorithm for linear inverse problems. The limitations, like there are two main major limitations of the model. First is the current way of computing the gradient of alpha is not scalable to a large number of transformation parameters, as it involves the expectation in which the number of samples s is needed to compute the integral scales exponentially with n, and the dimensionality of s. The second limitation is the various constraints on the transformation that can be learned, which include orthogonally, compactness, connectedness, and commutatively of the images. Though the author has shown in experiments that some of these theoretical constraints are not quite problematic, there are still some important transformations that cannot be learned as a result in unsupervised manner, such as global variations. In contrast, are a combination of rotation and translation. So finally, the key takeaways are in this work, the authors have studied the problem of disentangling factors, which is a famous problem in signal processing of various images, specifically discrete patterns versus continuous transformations. To approach the problem, they combine and take help of mathematical models. To approach this problem, the authors have combined and take help from various mathematical models, that is group theory and the Bayesian learning and sparse coding within a Bayesian model. So this is actually a combination of group theory and the sparse coding, which is the famous problem for which is the baseline for dictionary learning. So they show how spatial patterns and transformation can be learned as separate generative factors and inferred simultaneously. So when the model is trained on synthetic MNIST datasets containing known geometric transformations, the digits are learned by dictionary templates, and the applied transformation are learned by a transformation operator, providing a proof of concept demonstration of the um, feasibility of the combining Lie group transformation learning and sparse coding theory. Thank you.
Okay, so in this small presentation, I will show the demo of the code. The code is actually lengthy, but I will try to wrap up in 4 to 5 slides, such that the main part of the code is presented in this presentation. So let's start. The first part that was important was the plotting psi. The psi is actually the dictionary which was incorporated during the random initialization, where we have seen that the author have initialized that w matrices and psi dictionaries for each of the MNIST digit. That is, the psi is actually initialized for a total of 10 digits, and each digit has its own own dictionary collection of different transformation and translations. Okay, so this is what we want to plot here, like the image, the result of this code is shown in the report as well. So plotting psi is nothing but plotting all the dictionaries for each of the transformation and translation applied on each of the MNIST digit. Okay, this is the part where it shows the dictionaries when you command that plt.im show, that is image show of psi, and rest of the things are processing the images only. Second thing is plotting W matrices. See, psi and W are actually updated continuously in the learning algorithm. So we are plotting only the best values of W and best values of psi, such that it represents the actual reconstruction of all the images. Okay, so plot W is used to plot the W matrix, that is the weights vector, such that the, that is finally learned W matrix is plotted using the plot w function, and the result or the output of this part of code is also shown in the report, that is plotting w. See, w is plotted for different transformation translations. Okay, like the weight matrix for 2D translation and scaling is also presented. Then W matrix for only rotation is also presented, that is minus 75 degree to plus 75 degree. So we are getting multiple inner representations or deep visualizations using this plot. Okay, using this plt.imshow w vector, and we are plotting this w vector for w matrix for each of the each of the different transformation and translations that has been applied on our original MNIST dataset. Okay, so plotting operator is a different thing than what we have seen so far, because plotting operator consists of plotting actually the images, or what you can say is like the images that are reconstructed and compared with the original data set. Like let's say we have shown, or we have printed, or we have given the output of MNIST digit 5. Now we have original image of the same digit 5. Then we are also trying to reconstruct the same image 5 along with the inner representations and different images of the same value, such that the optimal one is selected final. And that is how we are concluding our reconstruction using that operator. Plot reconstruction is nothing but it is plotting the reconstruction image, or the reconstructed image of the original image, such that it it is actually resembling same features as of the original one. And the main part here is like calculating the useful variables, where it shows this or sparse coding, like group sparse coding, where we compute the auxiliary variables to calculate the useful variables. And this is the learning code, or the learning algorithm, where we start with the loop of iterating through the number of batches. And again, yes, we have initialized some random valued parameters or hyperparameters, and we are tuning those parameters such that we minimize the loss function. And we want to actually reconstruct the same images that has been that has been shown to us already. But with the lie group sparse coding, we want to show that, like even if we have presented our learning algorithm with plus minus 15-degree rotations, our learning algorithm with lie group sparse coding should be able to recognize more broader, or what you can say, large rotations and transformations. This has been done in unsupervised manner, such that our learning algorithm actually start to classify correct with correct labels, with more valued rotations than what the learning algorithm was presented earlier. Okay, so this is what maximum posteriori algorithm is trying to do here. And using fista algorithm, fista we have already seen in summary. So that is all.